In this video, we discuss extrema of a function on an interval I. Extrema are just minimum values and maximum values of that function. We'll define the terms absolute maximum, absolute minimum, relative maximum, relative minimum. Extrema in general, which just is local mins, local maxes, global mins, global maxes. Critical numbers, and we'll define the extreme value theorem. We'll talk about what it says, and we'll talk about how to apply it. So here's the definition. We want f to be defined on an interval I, and we want that interval I to contain the x value of c. F of c is the absolute maximum or the global, or excuse me, absolute minimum or the global minimum of f on that interval if f of c is less than or equal to f of x for all x on that interval. Now remember, f of x just represents the y values. So this is just saying that f of x, or excuse me, f of c is the smallest y value on the interval because it's less than or equal to all the other y values. F of c is an absolute max if it's greater than or equal to all of the other y values on the interval. I have a tendency to use the terms absolute minimum and absolute maximum rather than global minimum and global maximum, but they mean the same thing. Different teachers prefer different terminology, but you want to be familiar with both because different textbooks, will use these different terms. They're just interchangeable. That's for absolute extrema. Now, when it comes to relative extrema, we're talking about the lowest point or the highest point, the lowest y value or the highest y value in some neighborhood. So we say that f has a relative minimum or a local minimum, f of c at x equals c, if there's some h value greater than 0 such that f of c is less than or equal to f of x for all x value in some interval centered at c. So we go h units to the left of c, h units to the right of c, and that's our interval. If this is the smallest y value in that interval, then we call that a relative min. If f of c is the largest y value in that interval, we call that a relative max or a local max. When you're looking at the graph, though, you just look for the high points and low points. It's actually really simple. And when we're talking about a function defined on a closed interval, we include the points on that closed interval as well. So this black curve represents the function y equals f of x. Looks like a polynomial function. It's well defined for all real numbers, but we're only interested in finding relative and absolute extrema on the interval from a to b. So we just look at this point at x equals a and we say, is that the highest point nearby? And it is. It's larger than all the other y values on the interval that we're interested in. So f of a is actually a relative max. And then we say, okay, I'm looking for highs and lows. Here's a low point. F of c sub 1 is a relative minimum because it's smaller than all of the other y values nearby. So this is a relative min. And this one is a relative max. And then at c sub 2, we've got a relative max because that's the largest y value in the neighborhood. C sub 3, we've got a relative min because that y value is smaller than all the neighboring y values. And then here at B, we've got a relative max because that's the largest y value in the neighborhood. Now, when you're talking about the absolute extrema, absolute minimum, and absolute max, it's always going to be one of the relative extrema, one or maybe multiples if there's more than one x value that maps to that same y value. But from this graph, it looks like the largest y values, or the two relative maxima that are possible absolute maxima occur at x equals c sub 2 and x equals b. But if I drop a sort of perpendicular line to the y-axis, I can see that this y value at x equals b is smaller than the y value at x equals c sub 2. So f of b is less than f of c sub 2. So this relative max is actually a global max or an absolute max as well. And then the smallest y value on the interval is probably competing between these two relative minima. But if we look at where those relative minima meet the y-axis, if we think about sort of dropping a perpendicular line from our point on the curve to the y-axis, we see that this y value is actually larger than this y value. So we're looking for the smallest one for the absolute min. So this one is the absolute min. The absolute min occurs at C sub 3. Okay, now when you ask about relative minima and relative maxima, the C values or the X values are the locations where those maxima or minima occur. But if somebody asks you for the maximum value of the function, they're asking you for the corresponding Y value. So the relative max is actually this number f of A, whatever that number happens to be. And the absolute max of the function is f of C sub 2, whatever that number is, and the absolute min is f of C sub 3. Critical numbers are defined in this way. First of all, they have to be in the domain of your function. If that function has a derivative of 0 at C, or f prime of C is undefined, then we call C a critical number of the function f. So critical numbers are all the points where the slope is either 0 or where the derivative is undefined. If we look at the tangent lines here and here and here, they're all going to be horizontal. I could draw a tangent line. It's going to be tangent to the graph, and it would be a horizontal line with the equation y equals f of C sub 3. And this one would be a horizontal line as well with the equation y equals f of C sub 2. So since we've got a horizontal tangent line here and here and here, C sub 1, C sub 2, and C sub 3 are critical numbers. Now, it's also possible that the derivative might not exist. So here's an example where the derivative doesn't exist. Maybe it's nice and curvy, but then we have a little sharp corner there. Maybe that corner occurs at x equals 3. That's a point where the derivative does not exist. So we'll say f prime of 3 does not exist. So x equals 3 is a critical number of this function. This is y equals f of x. And then this one also has two other critical numbers. The critical number that corresponds to that x value and that x value. Maybe this is x equals 1.5, and maybe this is x equals negative 0.5. So f prime of 1.5 from our picture is 0, because that has a horizontal tangent line. The slope is 0 there. So x equals 1.5 is a critical number. And f prime of negative 0.5 is equal to 0 there. So x equals negative 0.5 is a critical number. So here's a theorem. It says all of the relative extrema occur only at critical numbers. So if you have an extrema, so if you have an absolute maximum or an absolute minimum, either the derivative is 0 or the derivative is undefined. And actually, I guess we should say this is relative extrema on the interior of an interval. So not at the endpoints, occur only at the critical numbers. We can have relative extrema at the endpoints. This is definitely the largest y value in the neighborhood, and this is definitely the largest y value in the neighborhood. But when we're talking about a function that's well-defined for a large interval of values, maybe all real numbers, for example, or if we're talking about, well, just finding relative and absolute extrema in general, we're talking about finding those points where the derivative is either 0 or the derivative is undefined. Those are possible locations for relative extrema. Now, not every relative extrema, or not every point, not every critical number is a relative extremum, but every relative extrema corresponds to a critical number. So if you're at a relative max or a relative min on the interior of an interval, then either f prime equals 0 or f prime is undefined. But it's also possible that you could have like a flat spot on your graph, and that would correspond to a critical number where the function does not have an extreme value. So maybe we've got a graph like this. Looks kind of like a cubic graph. Might have a horizontal tangent line at x equals 2. So f prime of 2 is 0. So x equals 2 is a critical number of this function. But f of 2 is not a relative extrema. It's not a relative min or a relative max, because that function is increasing the whole time. It's increasing and then it has 0 slope and then it's increasing again. So if it has a flat spot where it does that, where it's increasing and then 0 slope and increasing, or it goes from decreasing to having a 0 slope to decreasing, then you won't have a relative extrema. But notice that all these other values, wherever we had a slope of 0 or a slope that was undefined, we did have a relative extrema. Well, yeah, we had a relative extreme value. Extremum is singular. This is a relative min, and the derivative is 0 there. It's the smallest y value in the neighborhood. This is a relative max. This derivative is 0 there. It's the largest y value in the neighborhood. This is a relative min. It has, it's the smallest y value in the neighborhood, and the derivative is undefined there. So these three x values, -0.5, 1.5, and 3, are all critical numbers. And in this case, in this example, all three of them happen to be relative extrema. These are relative mins, and that's a relative max. But again, you could have a critical number like this, where you have a slope that's 0, that is neither a relative min nor max, because the slope goes from positive to 0 to positive, or positive to 0 to negative. Like, it just keeps increasing and then flattens out and increases. So it's not the smallest y value in the neighborhood. Yeah, I guess we could be more specific and say, is it a relative min? No, because there are y values nearby that are larger than it. Is it a relative max? No, because there are y values nearby that are smaller than it. So it can't be either of those, but the slope is still 0 there. So it's still a critical number. So all critical numbers are possible locations of relative extrema. They are possibilities. But the function just has to have the right shape. It actually has to be it has to correspond, that critical number has to correspond to either the largest y value in the neighborhood or the smallest y value in the neighborhood to qualify as a relative min or a relative max. And then if you're on a well-defined interval like this, including the endpoints, then it's also possible that you can have a relative max or a relative min at the endpoint. And the absolute max and the absolute min are just the largest y values on that list of y values that you found. So here is a theorem, extreme value theorem. It says if f is a continuous function on the interval from a to b, then f has an absolute maximum and an absolute minimum on that interval. You might say, okay, well, how can that theorem fail to apply? Well, you might have a discontinuity. So maybe the function is well defined on the interval from a to b, but it looks like this. Maybe this is our interval from a to b. So it has an asymptote at x equals c, or it would have had an asymptote, but then somebody said, I want to define the function at x equals c. So they just said at x equals c, the function value is whatever, and they plugged in a point. So now this function is well defined on the interval from a to b, but it's not continuous. Now, does it have an absolute max or an absolute min on the interval? It certainly doesn't. The function actually goes to positive infinity and negative infinity on that interval. So the extreme value theorem doesn't apply because the function's discontinuous. You have to draw it in 3 pieces, number one. But and so because the function's discontinuous, we wouldn't expect the function to have an absolute max or an absolute min on that interval. Another possibility for not having an absolute max or an absolute min is having a function that is well defined on an interval from a to b, not including one of the points. So here's a function that actually has an absolute max and absolute min on the interval of interest. but the theorem doesn't hold for that function. We say if the function is continuous on the interval from a to b, then it has an absolute max or an absolute min. Does this function have an absolute max or min? No, it goes to negative infinity and positive infinity. So that's not possible, but I guess my point is the theorem doesn't even apply because the function isn't continuous on the interval. So we'll say f is not continuous. So the extreme value theorem does not apply. In this one, we've got an interval from a to b, but that interval is not closed. We've got y equals f of x, and we're looking at it on the interval from a to b, including a, but not including b. In this case, the extreme value theorem does not apply. Because b is not in the interval that we're interested in. It's not in the interval I. That interval has to be a closed interval. But the function still has an absolute max and an absolute min. The absolute max occurs right here at f of a, and the min occurs at that critical value, whatever that is. I'll just call it c. F of c is the absolute min. So it's possible to have an absolute max or an absolute min, even if the theorem does not apply. But what the theorem says is if f is continuous on a closed interval from a to b, then we're guaranteed that it has an absolute maximum and an absolute minimum. So there are really two things you have to check. You need to make sure it's continuous and make sure that the interval is closed. If both of those things are true, then you're guaranteed that you'll be able to find an absolute max and an absolute min on the interval. If the function's discontinuous, there are no guarantees. You might have an absolute max or minimum, or you might not. If the function or if the interval is not closed, if it doesn't include those endpoints, you might have an absolute max or minimum, or you might not. So it really just depends. Here's another one that I saw in the book. So here's on the interval from a to b, we've got a function. And maybe at c, we've defined the function value to be something else. So it looks a little bit like a parabola, but has an open circle at the point where it would have a minimum. This function's discontinuous. So the extreme value theorem does not apply because we've got a removable discontinuity at x equals c. I could redefine the function, just coloring in that circle, where I make the function value equal to the limiting value as x equals c, or as x approaches c of the original function. And then this theorem would apply. We could make the function continuous by redefining the function in that way. But since the function is not continuous, we're not guaranteed anything. But you could still ask yourself, well, even though it's not continuous, it might still have an absolute max or an absolute min, does it? And it does. We've got an absolute max right here. F of A and F of B happen to be the same thing. So you've actually got two, well, you only have one absolute max, it's that value, but you've got two x values where that absolute max occurs. They occur at the endpoints. And then it has no absolute min. Because it would have been this limit, but we never actually get there. We get infinitely close, arbitrarily close to the limit, that limiting value, the limit as x approaches c of f of x, but we never actually get there. So this function doesn't have an absolute min. So I think just looking at these pictures, I think intuitively the extreme value theorem makes sense because what it's saying is if you are on a closed interval from a to b and the function is continuous, well, then we're guaranteed to have an absolute max and an absolute min. On the interior of the interval, the absolute or the possible locations for absolute extrema occur at the critical values. So we've got a critical value here, and a critical value here, and a critical value here, and a critical value here. But then there's also the possibility that our absolute max or absolute min could occur at the endpoints, so f of a and f of b. But if that function is well-defined on a closed interval, it's continuous, you can draw the entire thing without lifting up your pencil, then we're guaranteed to have an absolute max and an absolute min, and the relative extrema, let's just say the extrema, let's say extrema occur at critical values or critical numbers. Critical numbers and critical values are interchangeable depending on the textbook author, or at the endpoints. Let's say and at the endpoints. So if I look at this picture and I try to label everything, this is a relative max. This is also a relative max. This is also a relative max. So all three of those are relative maxima. Actually, I think that there's one other critical value, isn't there? Right here at the bottom. And then if that's a minimum, this is a little higher, that's a relative maxima as well. The relative mins occur here and here and here, the corresponding y values. And the absolute max is the largest y value, so it's that one, whatever that y value is at x equals a. And the absolute min is the smallest y value, which happens to occur on the interior. So our largest y value could occur at the endpoints. Our largest and smallest y values can occur at the endpoints, or they can occur on the interior of the interval. I mean, they might occur on the left or the right or inside. That's why we have to check all the critical numbers and then the endpoints themselves. But remember, it's possible that if you're at a critical number, that you just have a flat spot, that you might have a critical number that corresponds to just a point where the derivative is zero, where the function goes from increasing to increasing or decreasing to decreasing, but it goes through zero. That won't correspond to a relative minima or maximum, but it will still be on your list of critical values. Okay, so that's the concept. Let's apply it to a particular function. I've got f of x equals x cubed minus 3x squared plus 2, and we're asked to find a relative and absolute extrema on the interval of interest. Well, the first thing that we typically do when we want to find relative and absolute extrema is we find the critical numbers. So remember, critical numbers are those places on the graph where we have a derivative equal to 0 or a derivative that's undefined. So to find the critical numbers, we will compute f prime. Derivative of x cubed is 3x squared, just using the power rule. Bring the exponent down, multiply by x to the 1 less power. Then we subtract 3, and then we multiply by the derivative of x squared, which is 2 times x to the 1 less power. You bring the exponent down, multiply by x to the 1 less power, and then the derivative of 2 is 0. So if we simplify that, we get 6x squared minus 6x. And you can factor that. These two terms have a 6x in common. 6x times x gives me my first term. 6x times -1 gives me my second. So that's f prime. And we're searching for critical numbers, right? So we want to know where the function or where the derivative is equal to 0. And after we factor it, we set f prime equal to 0 and solve for x. We've got 6x times x minus 1 equals 0. This times this equals 0 if one of the factors equals 0. So either x equals 0 or x equals 1. Those are two critical numbers. You also want to look at that derivative and ask yourself, are there any x values for which that derivative is undefined? You say no. That derivative is well defined for all real numbers. So I think we're good to go. These are the only critical numbers of f. Now, if I want to find the relative and absolute extrema of a function on an interval, I find the critical numbers and I evaluate the function at the critical numbers to find the y values there. And then I also evaluate the function at the endpoints. So we need f of 0. That's 0 cubed minus 3 times 0 squared plus 2, which is of course just 2. We want f of 1, which is 1 cubed minus 3 times 1 squared plus 2. So 1 minus 3 plus 2, which is 0. And then we also want the, oops, I think I made a mistake. Do you guys see my mistake? This is 3x squared minus 6x. So that should be a 3, and that should be a 2. Whoops. Okay. There we go. I found my mistake. So x equals 1 is not a critical number. Sorry about that. We want f of 2. So you have 2 cubed minus 3 times 2 squared plus 2. So that's 8 minus 12 plus 2. Negative 12 plus 2 is negative 10. Negative 10 plus 8 is negative 2. And then we also want to evaluate f at the endpoints. So our endpoints are negative 1 and 3. Negative 1 cubed is negative 1. Negative 1 squared is 1. So we have 1 times negative 3, which is negative 3 plus 2. I have negative 4 plus 2, which is negative 2. And then f of 3 is 3 cubed minus 3 times 3 squared plus 2. That's going to be 27 minus 27 plus 2. So we get a 2. So we've got two y values, actually. Y equals 2 and y equals negative 2. The smallest ones on the list are minima. And since I only have, or the smallest y values on the list are the absolute mins. There happen to be 2 x values that map to those absolute mins. And the largest y values, which are 2, both equal to 2, are absolute maxes. And we can graph this now. At x equals negative 1, y is equal to negative 2, right? And at x equals 0, y equals 2. And at x equals positive 2, x equals negative 2. And at x equals 3, y equals positive 2. And I did accidentally find this value, f of 1 happens to be 0. So it's going to look something like this. And we know polynomials are nice and smooth. That's why I'm drawing a smooth curve. So that's our graph. And here are our absolute maxima. We have an absolute maximum value of 2 at x equals 0 and x equals 2. And then here we've got absolute minimum values. At x equals -1 and x equals, this is x equals 2. That's actually x equals 3. Sorry about that. All right. Now we can see all of this on the computer as well. I want to show you how to come up with these graphs on Desmos.com. But this is basically your procedure for finding absolute and relative, or excuse me, for finding absolute extrema. Talk more about relative extrema later. This is how you can find the absolute max and absolute min of a function on an interval. You find the derivative, you set it equal to 0, and then you solve for x. And then you also look for any x values where the derivative is undefined. Since our derivative is a polynomial, it's well-defined everywhere. The only critical values are these two. You evaluate the function at the critical values, you evaluate the function at the endpoints. The largest y value is your absolute max, the smallest y value is your absolute min. Remember, the y's are the mins and maxes, and they occur at particular locations. Those locations correspond to the independent variable. Now, this is just part of our graph. The rest of the function actually looks like this. It's a cubic polynomial, so it's going to have that shape in general. And y is equal to x cubed minus 3x squared plus 2. Let's look at the same graph on Desmos.com. We'll see basically the same picture. Our goal in calculus is that you'd actually be able to graph this yourself and understand what the function looks like just from understanding the algebra and all of this symbolic manipulation. But the graphs online confirm that we're correct. Okay, so we had our function y equals x cubed minus 3x squared plus 2, and we're only interested in that part of the function on the interval from -1 to 3. So this is how we type it into Desmos.com to get a graph of that function. But I like to graph the entire function as well. So the whole graph looks like that, but the part that we're interested in is that interval, is on that interval from -1 to 3. Oops. So I want to zoom in a little bit. And I think I want to get rid of the grid for a minute. And now you can see that the absolute extrema are going to occur at x equals 0 and x equals 3. Those are your maxes. And the absolute minimums occur at x equals -1 and 2. Those are your mins. You can see it on the picture. But one way that we can verify that is typing in these functions. So this is our function, and we're interested in the function values on that interval from -1 to 3. So I like to plot the points and label them. At x equals -1, the y value is -2, and at x equals 3, the y value is also, or is equal to +2. Then we compute the derivative. Now, the functionality on Desmos does not allow us to find the derivative. Desmos doesn't compute the derivative for us. So I just typed f sub prime of x, and then I computed the derivative just using the power rule. So we bring the power down, multiply by x to the 1 less power. So you've got 3 times x to the 3 minus 1, which is 2. And then we have this -3 times x squared. So you've got -3 times the derivative of x squared when you compute the derivative of that term. So you have -3 times 2, which is -6 times x to the 1 less power. The derivative of the constant 2 is 0. So you type that in. But again, we're only interested in that part of the graph or part of the derivative where x is between -1 and 3. So I graph that. And at first, it's not obvious that that's only the part between -1 and 3. But if you zoom out a little bit, you can see that you're just getting that part of the parabola. Now, if we add the grid lines now, you can see a little bit better what our slopes are. So our critical values occur where the derivative is equal to 0, and we found that algebraically by factoring 3x squared minus 6x and setting each factor to 0 and solving for x. We had x equals 0 and x equals 2. Those are the the zero values on this orange graph. The orange graph is the graph of the slope. So the slope is 0 at x equals 0 and x equals 2. And I think we can see that if we look at the original teal graph itself. If we draw the tangent line and let x vary, that tangent line has a 0 slope at x equals 0. And there's the 0 slope. It's the calculator is actually computing that for us. And that tangent line has a 0 slope at x equals 2. So the orange graph is actually giving me the slope of that tangent. And we can see that horizontal tangent line there and how it corresponds to that 0 value on the derivative. And we can see the horizontal tangent line over here and how that corresponds to that 0 on the derivative graph. But so we find two critical values. They occur at 0, x equals 0 and x equals 2. And then we evaluate the function there. And then we say let's ignore the derivative for right now. The largest y value on this list is our maximum. The largest y value is 2, and it occurs at x equals 0 and x equals 3. And the smallest y value is our absolute minimum. It occurs at x equals -1 and x equals 2, and they're both equal to -2. Usually you have only one absolute maximum or absolute minimum, and actually we do in each case, or in this case, we have only one absolute max, it's 2. We have only one absolute min, it's -2, but it just happens to occur at more than one x value. It's not usually this obvious, or it's not usually, you don't usually have a pattern like this with, two absolute maxes and two absolute mins. It's just sort of coincidence because of the symmetry of this particular function. But with this graph, we can also explore some other ideas. If we look at this graph and we look at the tangent line, we can see that the tangent line always has a positive slope. As at a equals -1, it has a very large positive slope. If I start here and I go up 1, 2, 3, 4, 5, 6, 7, 8, 9 units and 1 unit to the right, and I get a second point on my tangent line. So just using the grid, I know the slope of the tangent line at x equals -1 is actually equal to 9. If I look at the derivative function, you see that our derivative is consistent with that. We've got a slope of +9 at x equals -1 according to that derivative graph. But then as we let a increase, as a goes from -1 to 0, notice that the slope is decreasing. And you can actually watch that slope change right here on our on the left-hand side of the screen. But as that slope, or as our a value gets closer and closer to 0, that slope is still positive, but it's getting less and less positive. So the slope is decreasing until it gets to 0 when you're at 0. And so all of these slopes are positive, and they go from 9 to 0, but they get less and less steep as you go from 9 to 0. Or as you go from x equals -1 to x equals 0. As you go from x equals -1 to x equals 0, the slopes go from 9 all the way down to 0. Okay, and then the slopes in here are all negative. If I draw tangent lines on this side, all my lines are going to decrease as you go from left to right. So we have a bunch of negative values here. And that's consistent with the y values on the graph of the derivative. The derivative was positive, and it started at 9, and then it got less and less positive until it was 0 at x equals 0. And then between x equals 0 and x equals 2, our slopes are all negative. But we see that we have a maximum magnitude slope of -3. It's steepest at x equals 1. The slope appears to be -3 at x equals 1. So we go from 0 slope to a slope that gets increasingly negative until it gets to -3 right here. And then that slope increases from -3 back to 0 as we go to the other critical value, to that other extreme point. So we're going to let a go from 0 to 1 now, and we'll see that the slope is negative. So let's label that point as well. So we're here at the top, and then we let that a value increase from a equals 0 to a equals 1. And we look at the slope. Look at the slope on the left-hand side as well. That slope has a largest magnitude of -3 there. So that whole time as we were going from 0, as the slope was going from 0 to -3 and the x values were going from 0 to 1, that the slopes were decreasing. So the derivative itself was decreasing. But then after that point, the slopes are going to continue to be negative, but they're going to be less negative. So the slopes will be increasing on this interval from 1 to 2. So as we go from a equals 1 to a equals 2, the slopes go from -3 back to 0. Now, if you just look at the orange graph, you can see that the slopes are all positive on the interval from -1 to 0, and the slopes are negative on the interval from 0 to 1, or excuse me, 0 to 2, and they have a largest magnitude slope at 1, which is this one right here. And then they have a 0 slope at a equals 2. And then as x increases from 2 to 3, that slope is increasing as well. The slope gets larger and larger. It's going backwards and forwards. A little bit distracting, isn't it? But if you're on that interval from, let's see, 2 to 3. Oops. You can see the slopes are getting larger and larger and larger, which is consistent with that orange graph. And that's not related to finding absolute extrema. We're already done solving the problem that was asked of us, but I thought it was still a good exercise to think about the tangent line, to think about its slope and how it is, the slope of that tangent line is given by the orange graph, and how these trends, or where we have the functions increasing and the functions decreasing and then functions increasing again, that it corresponds to that sort of relationship between the derivative graph and the graph of the original function. Okay, so we've done that. Let's go back to the extreme value theorem. Red lines are a little bit distracting now. Let's use the extreme value theorem for a different function. So here we've got a rational function, g of x equals x, divided by the quantity 1 plus x cubed. We know 1 plus x cubed will equal 0 and x equals -1. So we're going to have a vertical asymptote at x equals -1. And let's say we're interested in this function on the interval from -2 to 4. So we're on that interval. Now the extreme value theorem doesn't apply because we've got an infinite discontinuity at x equals -1. But we might be asked for relative and absolute extrema. Well, I know I don't have absolute minima or absolute maxima because the function goes to positive infinity as x approaches -1 from the left, and it goes to negative infinity as x approaches -1 from the right. But we can still find relative extrema if we compute the derivative of this function, set the derivative equal to 0, and find those x values where the derivative is 0. We can also look at the y values at the endpoints and compare those to find absolute and relative extrema. But again, because this function has a vertical asymptote and the function approaches positive infinity on one side of the asymptote and negative infinity on the other, we don't have absolute extrema this time, but we might have relative extrema. So that's the original function, but that's just the part that we're interested in. So maybe we might graph it like this. Now we're particularly interested in the function values at the endpoints. So x starts at -2 and ends at 4. So we'll evaluate the function at -2. And we'll evaluate the function at 4. And I'm graphing ordered pairs. So the y value here is approximately 0.286, and the y value here is 0.062. Now it looks like I've got a possible absolute extrema, or excuse me, relative extrema right there. Whatever that maximum value is, it looks like 0.794. But the extreme value theorem doesn't apply in this case. We can't find absolute extrema. We just might be able to find a relative extrema. In order to do that, we'll use our paper. We'll compute the derivative. Actually, we'll just type it. Let's type g prime. The derivative can be found using the quotient rule. Remember, the quotient rule says you have the bottom function, it's low d high. Low times d high, the derivative of the top function is 1, minus high, which is x, d low. The derivative of 1 is 0. The derivative of x cubed is 3x squared. All divided by low. So 1 plus x cubed, quantity squared. Oh my goodness. So that's your derivative graph, or your derivative function. We're only interested in it on the interval from -1 to 3. Kind of funny, I don't see it on the interval from, I said -1 to 3. I think it was actually -2 to 3, or -2 to 4, 2 to 2. So this is our derivative. And you might say, okay, well, where is the derivative equal to 0? The derivative is equal to 0 right there at 0.794. And the slope is 0 on this one at 0.794. The y value is 0.529. So it looks like we have a relative max of 0.529 at 0.794. That's the x value that causes this expression to be 0. Now, typically, if I were doing this on with pencil and paper, I would simplify this. This is 1 plus x cubed minus 3x cubed. That simplifies to 1 minus 2x cubed. So that function will equal 0 when the numerator equals 0. So it looks like x cubed is going to equal 1/2. So x is equal to the cube root of 1/2. And let me actually check that. 1/2 raised to the 1/3 power. I don't actually know how to do the cube root on Desmos. Yep, that's the same value. What was it? 0.794, or approximately 0.7937. It's actually at 1/2 to the 1/3 power. So that's where we have a relative extremum. But we can only, and the reason we can tell that is because we can look at the graph and see it. But again, if we didn't know what the graph looked like, it might just be that there's a flat spot there. We just know the derivative is 0, but we don't know if that derivative of 0 corresponds to the largest y value in the neighborhood or the smallest y value in the neighborhood. Turns out when we look at the graph, we can see that it corresponds to the largest y value in the neighborhood. But if we didn't have the graph, we wouldn't know that. Yeah, the extreme value occurs at is 1/2 to the 1/3 and g evaluated at that value. And if we evaluate g prime at that value, we'll see we get 0 there. Now, another way that you can tell whether you have absolute or relative extrema is to look at the derivative graph. And we're going to talk about this more in another section. But notice that the derivative is positive on this side, and then it's 0 at that 1/2 to the 1/3 power, and then it's negative on the other side. If the derivative is positive, that means the function is increasing because all of our tangent lines are going to have a positive slope. So the derivative is positive over here, and then it has a 0, and then the original function has a 0 slope, and then the derivative is negative here. And you can see that on the corresponding derivative graph. Like the teal graph is positive before that orange dot, and then it's negative on the other side of that orange dot. That corresponds to the original function being increasing and then having 0 slope and then being decreasing. Since it goes from increasing to decreasing, we know we're at a relative max. That's sort of a preview of what's called the first derivative test. We'll talk more about that later. But those are our first two examples for the extreme value theorem. The extreme value theorem itself doesn't apply because the function has an infinite discontinuity at x equals -1. But we can still explore for relative extrema. Let's get rid of that derivative value. We have a relative minimum here at x equals -2 of 0.286. We could just plug in -2 and get an exact answer if we wanted. We have that's a relative minimum. It's the smallest y value nearby. And then at x equals 4, we also have a relative minimum of 0.062. If we wanted to get the exact value, we could plug x equals 4 into the original function. And then we have a relative max here at approximately 0.794 or 1/2 to the 1/3 power. And the corresponding y value is that relative max. We know it's a relative max because the derivative goes from being positive to being 0 and then to being negative, as we saw when we looked at the corresponding derivative graph near that point. So we are able to just visually determine the relative extrema, but without the graph, we wouldn't necessarily know. Since the extreme value theorem doesn't apply, if I didn't have this graphing calculator, I probably wouldn't be able to find that point. It's still a good exploration for us, though. We were able to find a relative max and two relative mins and determine that the function does not have an absolute max or absolute min on the interval because it has an infinite discontinuity. I think I'll stop there. We'll do more pencil and paper calculations in the next video. We'll look at a function with rational exponents, and then we'll look at the graph on Desmos.